Welcome to the 8th lecture of our Introduction to Modular Forms. So, last time we proved the linear independence of E4 and E6, right? And, well, not just linear independence. I think we proved the algebraic independence of E4 and E6, right? So, and since like if like if M sub k denotes the space of modular forms of weight k, then it has a like Eisenstein basis that it looks like this: E4 to the A E6 times E6 to the B, right? Where 4A plus 6B equals to k. So this is the Eisenstein basis. And since E4 and E6 are algebraically independent, so we can say that, well, the space of all the modular forms is isomorphic to C, E4, E6, right? So this is the polynomial ring with uh, the variable of the polynomial being E4 and E6. So this is the space of all the modular forms, right? So yeah. So also, if we remember, I think a couple lectures earlier, I think we proved that if f is a modular form of weight k, then the function f of z, the modulus of f of z times the imaginary part of z raised to the power k over 2. We prove that this is an SL2z invariant function, right? Meaning that this is exactly equal to f of gamma z, imaginary part of gamma z to the power k over 2 for all gamma b in SL2z, right? Proved it, and today we'll prove something related to this. So, we are going to show that, well, we are going to basically check whether the converse is true. So f in mk implies this is true, but does the converse hold? So, so one way to think about it is that when we are taking modulus, we are losing some information, right? So, but turns out we are not losing too many informations. So, we can almost recover the modularity condition from this. So, let me state the theorem first, then we'll try to prove it. So, the theorem states that, well, it's actually a more general result. Let's say this is capital gamma. Capital gamma is a subgroup of SL2R. So it's actually a more general situation. So we are mostly interested in SL2Z, and SL2Z is a subgroup of SL2R. So we're good, right? So gamma is a subgroup of SL2R, and F is a holomorphic function on the upper half plane. Then the following are equivalent. What are the equivalent statements? The first one is f of z, imaginary part of z to the power k over 2 is gamma invariant. And the other one is there is a homomorphism that is chi from gamma to the unit sphere S1 such that f of gamma z equals to chi of gamma times cz plus d to the power k f of z, and what are c and d? C and d are just the lower row entries of gamma. So the theorem states that if the function, the modulus of f of z times imaginary part of z to the power k over 2, if that is SL2z invariant, then we can almost recover the modularity condition, except we have a term with modulus 1 here. right? And this homomorphism, chi from gamma to S1, is called a character of a character of the group gamma. Okay, many authors call it a Dirichlet character. Yeah. So we are going to prove this theorem, but let us let us state some observations. That is, this theorem basically motivates us to define a more general notion than modular form. That is, modular form with character. So modular form with character. So the definition is almost identical. So the modular form with character must be holomorphic and it must be bounded as the imaginary part goes to infinity. The only change we are having is in the modularity condition. That is, we need to have this f of az plus b over cz plus d is equal to cz plus d to the power k f of z, but this time we have a character in front. So this is the definition of a modular form with character. Okay. Okay, let us try to prove the theorem first, then we'll state another interesting fact. The proof of theorem. Uh, yeah. So we have to prove that like 1 implies 2 and 2 implies 1, right? So 2 implies 1 is pretty obvious, right? Because we proved that if f is a modular form, then the modulus of f of z times imaginary part of z to the power k over 2 is SL2z invariant. So the proof is almost identical to that, but this time we have a term of modulus 1 in front. So the direction of 2 implies 1 is trivial, and there are some yeah. Yeah, so when we prove that if f is a modular form, then this function is SL2Z invariant. Then, in that case, our group was SL2Z. But this time, it's a subgroup of SL2R. So, but the arguments we gave for that proof, those arguments also work if the entries of our matrix are real numbers. Okay, so those details are left as an exercise. So I'm going to basically do part 1 implies 2. Okay, so let's do 1 implies 2 and exercise to fill out the details. Exercise. Okay, so yeah. Again, if f is identically 0, then the problem is trivial, right? If f is identically 0, then we can basically take like chi to be the like any homomorphism, right? We can even take the trivial homomorphism that takes all the members of this group gamma to the identity element of S1. So if f is identically 0, then 1 implies 2 is obviously true. So let us assume f is not identically 0. So suppose f is not identically 0. Then what happens? Then, well, we know that f of gamma z, imaginary part of gamma z to the power k over 2 is equal to f of z times imaginary part of z to the power k over 2. Okay, so this is given. We are given that this function is SL2Z invariant. Sorry, this function is gamma invariant. So this is true for all small gamma in capital gamma, which is a subgroup of SL2R. All right? Yeah. Now, what to do? Now, we shall basically do that. Well, f of gamma z is equal to, let us rearrange stuffs. Imaginary part of z divided by imaginary part of gamma z to the power k over 2. Right. Now, can someone tell me what is this thing? What is this ratio of imaginary part of z over imaginary part of gamma z? So let's say gamma is like A, B, C, D, where AD minus BC is 1, and now A, B, C, D are real numbers. Okay, then what is imaginary part of gamma z? That is imaginary part of AZ plus B over CZ plus D. And this is, what is this? Can someone tell me? Well, as before, we can basically do the same computation, right? So let's say if AZ plus B over CZ plus D, this is equal to CZ plus D mod square AZ plus B CZ bar plus D, right? Uh, uh, uh. Yeah. So if Z is, let's say, x plus IY and Z bar is x minus IY, we need to focus on the only on the imaginary part of this product, right? So what is the imaginary part of this product? So the imaginary part goes like, we have a IY from here, and yeah, so ADIY, then minus BCIY, right? And AD minus BC is 1. So and this is CZ plus D on square. So this is just imaginary part of Z over CZ plus D mod square. So this thing is f of gamma z mod is equal to imaginary part of Z over imaginary part of gamma z to the power k over 2 f of Z. So this is just CZ plus D to the power k f of Z. Is that right? All right. Yeah, now we are going to define two functions. Let's say one function is g of z, sorry. One function is, let's say, g of z, and that is defined as cz plus d to the power k f of z. And let's say another function is, let's say, h of z, which we define as f of gamma z. Okay. Right. And if we take the ratio of these two functions, well, first things first, we assume that f is not identically 0, right? That means there is an open ball where f is non-zero, right? So let's say there is an open ball B and f is non-zero everywhere in B. Okay. And G and H are obviously their holomorphic functions, and G and H are non-zero in B, right? So we can obviously take the quotient G of Z by H of Z. So this is also a holomorphic function on the, yeah, this is also holomorphic in B, right? And it has values in it has values in S1. Why? Because this quotient has absolute value 1. So this has values in S1. What does it mean? It basically means that, yeah, so if we invoke the open mapping theorem, since B is an open ball, the image of this holomorphic function has to be an open ball. given that this function is non-constant. Right? So the open mapping theorem says that the image of open sets are also open. But B is open, and yeah, and the image set of this function is some subset of S1. A subset of S1 cannot be an open set in the complex plane, right? So therefore, this function cannot be non-constant. So it must be a constant function. So let me state the argument again. The open mapping theorem states that if let's say f is non-constant, image of open set under f, image under f, image of open set under f is open, right? So if this function is non-constant, then its image of an open, so it takes an open set to another open set, right? So B is an open ball, so the image of B is supposed to be another open set, right? But we know that this function has values in S1. So the image of B is some subset of S1. We don't know which subset, but it doesn't really matter. But yeah, a subset of S1 cannot be open in the complex plane because S1, yeah, if we take like any point on S1, no matter how small an open ball we choose around it, that open ball obviously contains some points outside the sphere, right? So that is why this function must be constant. No. Yeah, so since this function is constant, we can say that, well, then f of gamma z is equal to alpha times g of z. What was g of z? G of z was cz plus d to the power k f of z. Okay, and where is this true? This is true for all z in B, right? Well, this is not yet true for all z in the upper half plane, but we're going there soon. Yeah, now let us define another function. That is f of gamma z minus alpha times cz plus d to the power k f of z. Let's call this function p of z. And obviously, let's say this is from the upper half plane. Okay, p is defined on all of the upper half plane, right? And p is 0 on the open ball B. Therefore, p is identically 0. Because if p is not identically 0, then the 0 set of p doesn't have a limit point, exactly. But since this is an open ball, obviously it has limit point. So p must be the constant 0 function. So since this is true, we can now safely conclude that, well, f of gamma z is equal to some alpha. Obviously, this alpha depends on gamma. Cz plus d to the power k f of z. Okay, and let's call this alpha chi of gamma. Okay. Now we just need to show that this chi defined like this is a homomorphism. Okay. All right. Let's say we take two matrices, gamma 1 and gamma 2, A1, B1, C1, D1, and gamma 2 is A2, B2, C2, and D2. Okay. Then f of gamma 1, gamma 2, Z is equal to chi of gamma 1 gamma 2 times, what is the lower row entries of the product gamma 1 times gamma 2? A2C1 plus D1C2, right? So times A2Z plus C1B2 D1D2 to the power K f of Z, right? Now let us compute this in another way. We can say this is f of gamma 1 times gamma 2 of Z, right? So this is chi of gamma 1 C1 gamma 2Z plus D1 to the power K f of gamma 2Z. Okay. Yeah, then again for this term we have another factor of chi of gamma 2. So chi of gamma 1, chi of gamma 2, and for this term we have C2Z plus D2 to the power K f of Z, and for this term we have C1 A2Z plus B2 C2Z plus D2 plus D1 to the power K, right? Chi of gamma 1, chi of gamma 2. Let us multiply this with this. Do we get the same thing? C1 A2Z and D1 C2, right? Yeah. C1 A2 plus D1 C2 Z plus D1 D2 and what is the other one? C1 B2. F of Z, right? So now if we compare this expression and this expression, we get that chi of gamma 1 gamma 2 is exactly equal to chi of gamma 1 times chi of gamma 2. So indeed chi is a homomorphism, so our proof is done. Okay, so now a natural question that arises is that, well, we are interested in SL2Z, right? We're interested in SL2Z. But how many characters of SL2Z are there? Okay. Do you have a guess? Let me tell you, it's a finite number. So I'm telling you that there are only finitely many characters of SL2Z. There is only finitely many homomorphisms from SL2Z to S1. Can you guess how many there are? A hint, that is, we've seen this number before. Yeah. So there are exactly 12 homomorphisms from SL2Z to S1. So why is a very good question. So uh, let me just sketch the proof of why there are only 12 homomorphisms from SL2Z to S1. So writing SL2Z like again and again is pretty difficult. So let me just call SL2Z G. And I'm going to define the commutator subgroup of SL2Z. So let us define the commutator subgroup that consists of all the terms of the form G1 inverse, G2 inverse, G1, G2 for all G1 and G2. No, this is not a set. So this is the set of generators. So the group generated by all the elements of this form is called the commutator subgroup. And this turns out to be a normal subgroup, so we can take the quotient G over H. And yeah, and as you can guess, this is a abelian group. because we are questioning out by the commutator of G1 and G2 for all G1 and G2, right? And I think this is called the abelianization of G, right? All right, yeah. So this is an abelian group, and yeah. So how many elements are there in G over H? So we're trying to answer this question. Okay. Again, do you have a guess? Yeah. So in modular forms, whenever you guess that like something has like exactly 12 of it, more often than not, you're probably correct. But why? Let us say that. So what is S for? Well, S and T are the generators of SL2Z that we have seen earlier. S was 1 minus 1 and T was this, right? And
This S4 is not force here.
no, this is S raised to the power 4. So multiplying this matrix S 4 times. This is identity. And we know that ST cubed is negative identity. Right? Now, yeah. In G over H, so in G over H, the image of S and T, well, in G over H, everything commutes, right? So in G over H, we have ST cubed is equal to S cubed T cubed. So, like this is not true in general. So here S means the image of S in G over H. That is the coset. So here S basically means that SH and T means that TH. The coset SH and the coset TH. So since in G over H everything commutes, this holds. And this is equal to like negative identity. And negative identity is equal to S squared, right? So therefore, S is equal to T to the negative 3. Of course, in G over H. Yeah. So if we raise it to the power 4, we get that T to the 12 is the identity. Right? Yeah. So G over the order of G over H is at most 12. Right? Because S and T are the generators of G, right? So all the elements of G over H are some cosets of some combination of S and T. So did I make any mistake? No, I don't think so. Yeah. No. Now, what is the order of T? So the order of T, yeah. The order of T is a divisor of 12, right? And T to the minus 3, no, sorry, T to the 3 is S inverse because T to the minus 3 is S, right? And this is not identity. Well, the coset of S inverse is not the identity coset H. So this is also left as, these details are left as an exercise. So I'm just sketching the proof. I'm not going through all the details, okay? So T to the 3 is not the identity, neither is T to the 4. Why? T to the 4 is S inverse T. If this has to be the identity, T must be equal to S. By that I mean that the coset of T is equal to the coset of S, which is also not true, and that is also left to the exercise. And neither is T to the 6. Why? Because T to the 6 is just S squared, right? And S squared is negative identity. And negative identity is not equal to the identity. So therefore, And the order of T is 12. So order of T is 12. The group has at most 12 elements, and the order of T is exactly 12. So therefore, the group has exactly 12 elements. And it's generated by one element. What do we call such a group? Cyclic group. So, and this group is precisely H, TH, dot, 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 T to the 11H. Right? Yeah. Now, uh, we have a very important observation. That is, if chi is a homomorphism from G to S1, so this S is not the S matrix.
This is circle.
Yeah, S1 is circle. Then if we take any number, sorry, if we take any matrix from the commutator subgroup H, the image of that element is going to be always going to be 1. Why? Because the elements of H are generated by which elements? G1 inverse, G2 inverse, G1, G2, right? So these elements generate H, and the image of these elements under chi is 1. Because the target group is an abelian group. So that's why the image of these matrices is 1. So therefore, like any combination of these matrices, they are also going to be like 1 under chi, right? So yeah. Right. Now, if we take, let's say, any x from G, okay, let's call it small g, okay, then the coset GH is equal to some t to the I h, right? So that means G times t to the minus I, sorry, t to the minus I times G is in H, right? So therefore, chi of G equals to chi of t to the I, because chi of this product is 1. So that is why. So that means if we take like and this is obviously chi of t to the power I. Okay. That means if we take like any element from the group, the only thing that matters is that in which coset is it in. All right. So we just need to figure out what chi of t should be. And we know that t to the 12 is in H. Because in here we have written that t to the 12 is the identity. By identity we mean that the identity coset. Okay, so t to the 12 is in H. That means chi of t to the power 12 has to be identity. So how many options for chi of t do we have? Exactly 12 options, precisely the 12th root of unities. Okay, so chi of t must be in the 12th root of unity, that is 1, and zeta 12 square, dot, 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 zeta 12 to the power 11. So these are the 12th root of unities. And the value of chi of t fixes the other values. Right? So there are 12 characters only. So even if we define a modular form with character, we cannot have more than 12 different kind of modular forms. Okay. So I find this very interesting. And also the fact that 12 arises every now and then. Yeah. So now we are going to see some very interesting results about how the coefficients of the Q series grows. So let's call this section coefficient estimates. So to begin with, let's start with our favorite modular forms. What are our favorite modular forms? The Eisenstein series, right? So what is the Q expansion of Ek? It's 1 minus 2k over bk times a sum, right? Okay, this sum is q to the n sigma k minus 1 of n. So what is the coefficient of q to the n here? This times some other constant, right? So let us ignore this constant for now. Let us just focus on sigma k minus 1 n. Okay, let us try to see how this function grows. Okay, so what is the definition of it? It's sum of d to the k minus 1 over all the divisors of n, right? So we can take n to the k minus 1 in front and get d of divides n. This is d over n to the power k minus 1, right? So this is n to the k minus 1 sum of d divides n 1 over d to the k minus 1. So this basically uses the fact that if d is a divisor of n, then so is n over d. Okay, and obviously this sum, this is smaller than, like, if we take all the d, if we take this sum over all the positive integers, so this sum is smaller than n to the k minus 1 sum of d equals to 1 to infinity 1 over d to the k minus 1, right? What is this sum? Exactly. So this is n to the k minus 1 zeta of k minus 1, right? And clearly, like sigma k minus 1 of n, this is at least n to the k minus 1, right? Because one of the terms in this sum is exactly equal to n to the k minus 1. So what do we see from this? That if n denotes the coefficient of q, sorry, if an denotes the coefficient of q to the n, then we get a bound for an, and that bound is precisely n to the k minus 1, n to the k minus 1, some constants, right? So therefore, the nth coefficient grows like n to the k minus 1, where k is the weight. Okay. But this is true for only for the Eisenstein series. So what about the other modular forms? So, and another interesting fact that is there is another special kind of modular forms that are called cusp forms. So the specialty of the cusp forms is that their constant term in the Q expansion is 0. So the way the coefficients grow for cusp forms and non-cusp forms is really different. So yeah, we're going to prove all those. Okay. So definition of a cusp form, definition of cusp form. So a modular form f of weight k is called a cusp form if A0 is 0 in its Q expansion. Okay. Mhm. And S over K is the space of all the cusp forms. Cusp forms. And and yeah, one can easily prove that S sub K is a vector space. Yeah. And what is the dimension of S sub K? No, it's not 12. Yeah. So what is the dimension of S sub K? Ideally, it should be related to dimension of M sub K, right? Since it's a subspace of M sub K. So what is it? So previously we have seen that the first, let's say the dimension of M sub K is D. So previously we have seen that the first D terms in the Q expansion are independent. So in S sub K, what are we doing? We are fixing the first coefficient. So among the D independent terms, we are fixing one of them. Exactly. Dimension of Mk minus 1. And yeah, it has a very straightforward proof, and that proof goes like this. So S sub K is the kernel of a map, kernel of, let's say, not F, sorry, kernel of, let's say, phi. What is phi? Phi is from Mk to C, and what does it do? It basically takes a modular form, and it, of course, it has a Q expansion, a n Q to the n, and it takes this to the first coefficient a0. Okay. So kernel of phi is S sub k, and yeah, and phi is a surjective map. That is why, using the first isomorphism theorem, we have M sub k quotient S sub k is isomorphic to C. So therefore, the difference of the dimensions of Mk and Sk is 1. Therefore, the dimension of Mk minus dimension of Sk is 1. Okay. Yeah. So we have just seen that if, uh, let me write it in below. So if an is the coefficient of q to the n in ek, then an grows like n to the k minus 1, right? Now we are going to prove a result for cusp forms. So let's state it. It states that let f be a cusp form, no, S sub k. Let f be a cusp form, then it's if its q expansion goes like this, sum of an qn. Of course, since the first coefficient is 0, the sum starts from 1, right? So if its an qn is the q expansion of f, then an grows like the, so an is of order n to the k over 2. So, so it basically states that, well, if we restrict the first coefficient, then the order of growth becomes like exponentially half. Like previously it was n to the k, now it's n to the k over 2. Okay, so let us try to prove it. So f is like this, a1q plus a2q squared plus so on, right? So near q equals to 0, we have that f of q is of order q. Because if q is very small, the latter coefficients get really small. So you can say that this is of order q. So that means f of z is of order e to the negative, e to the 2 pi I z, 2 pi I z, right? It's absolute value. And where is this true? This is true for like imaginary part of z goes to infinity. Like imaginary part of z being very large, right? Because if q is 0, that denotes that the imaginary part of z is 0, is infinity, right? And this is, if we compute this, becomes order of e to the negative 2 pi y, right? As y goes to infinity. So if we now take this f of z, y to the k over 2. So this is of order e to the negative 2 pi y to the k over 2. And if we now take the limit as y goes to infinity, what is this as y goes to infinity? Yeah. So as y goes to infinity, this goes to 0. So therefore, f of z y to the k over 2 is bounded. Okay, so I have a question. Why does this function going to 0 as y goes to infinity imply that this function is actually bounded? Well, yeah, but we have seen exactly this very result before, right? Because since f is a modular form, it takes all its possible values in the fundamental domain. So there exists a bound such that after this bound, this function is bounded by 1. And before this bound, this region is compact. So this function is bounded here as well. So it's bounded by some constant here, bounded by 1 here. So it's everywhere bounded. Okay. So therefore, f of z, imaginary part of z raised to the power k over 2 is bounded by some constant c. And this is true for all z in the upper half plane. Yeah. Yeah, now let us do this. F of x plus iy is equal to sum of an e to the 2 pi I nx e to the minus 2 pi ny. Right. Yeah. So from this, how can we extract the term an? I think we have done it in one of the previous lectures, using ideas from Dirac delta function, like multiplying by this and then integrating. So we are basically doing this f of x plus iy times e to the negative 2 pi I mx then we are taking the integral from 0 to 1. So again, we are swapping sum and integral because we can do it. So it's sum of an e to the minus 2 pi ny integral of e to the 2 pi I m minus, sorry, n minus m. It's n minus m x dx. And this is delta mn. So it's 0 if n and m are not equal, and it's 1 if n and m are equal. And this integral is from 0 to 1. And yeah, we can switch sum and integral because this sum is absolutely and uniformly convergent. Of course, it's the power series of a holomorphic function, so it's obviously absolutely and uniformly convergent. So you can swap this sum, and what do we get? We get a m e to the minus 2 pi my. Right? So what is am? Am is just e to the 2 pi my times the integral of f of x plus iy e to the minus 2 pi I mx. Right? Yeah. We know that this is bounded, so we can basically say that, well, let's take the absolute value on both sides. So am smaller than e to the 2 pi my 0 to 1 f of x plus iy, and the absolute value of this thing is, well, 1. So there goes this. And yeah, and we know that f of x plus iy times y to the, was negative k over 2 or just k over 2? Just k over 2. Just k over 2 is bounded by c, right? So this is bounded by c times y to the minus k over 2. So the integrand doesn't really depend on x anymore, so we can take it in front. So this becomes e to the 2 pi my times a constant c times y to the negative k over 2. Right. And this is true for all positive y, right? Now we are almost done. Here we can, so since it's true for any positive y, we can just take y to be equal to 1 over m. So if we took y to equals to 1 over m, what do we get? We get am is smaller than a constant c, then e to the 2 pi, then 1 over m to the power k, negative k over 2, that is m to the power k over 2. And it's a constant again. So therefore am is order of m over k over m to the power k over. And we're done. Okay. Yeah, I think we can take a 5-minute break now. Okay. We have another result, and that result is basically about the growth rate of the coefficient of non-cusp forms. That is, let's say k greater than 4 is even. Of course, we are dealing with those numbers, right? And if is, let's say, an q to the n is a modular form of weight k, then an grows within constant multiple of n to the k minus 1. Grows like n to the k minus 1 within constant multiple if and only if f is not a cusp form. Okay. So we have already seen one direction of it, that is, if n grows like n to the k minus 1, then it cannot be a cusp form, right? Because here we have written within constant multiple. So if an is of order n to the k minus 2, then obviously it's of order n to the k minus 1 as well. But when we are writing within constant multiple, it basically means that an is both small o of n to the k minus 1 and capital O of n to the k minus 1. So that is a stronger condition. So yeah, so we have already proved one direction of it. Let us try to prove the reverse direction. That is, if f is not a cusp form, then its coefficients grow like n to the k minus 1. Okay. Proof. Let's say f is not a cusp form. Okay, then what do? We basically do this f minus a0 of ek. So f is sum of a n q to the n, right? And what is the constant term of ek? So ek is 1 minus 2k over bk times sum of sigma k minus 1 n q to the n, right? So the constant term of ek is 1. So this one has constant term 0. So it's a cusp form, right? So let's say this is the cusp form, and therefore its q expansion goes like this, equals to sum of bn q to the n, where now this sum starts from 1, right? Okay. Yeah. Now what is the nth coefficient of f? The nth coefficient of f is exactly equal to bn plus a0 times the nth coefficient of ek, right? What is the nth coefficient of ek? The nth coefficient of ek is negative 2k over bk times sigma k minus 1 of n, right? Now we are basically done. Since f is not a cusp form, this is non-zero. And we know that bn grows like n to the k over 2. And this grows within constant multiples of n to the k minus 1, as we have seen earlier. So therefore, an grows within constant multiples of n to the k minus 1. Because it's a constant and it's also bounded by some constant. Okay. In a sense, what we are doing is that if we are given any statement about modular forms, what we do is we first prove it for Eisenstein series. Then we basically do some manipulation and basically given any modular form, we how can I say it? How to rephrase it? So basically, we remove some difficulties by translating the problem into Eisenstein series. Here as well, what we did with is that we first prove the result for cusp forms, right? So this basically guarantees us that this term is the dominant one. Right? Then we proved it for Eisenstein series. Then using these two, we basically combined and got the Yeah, got the general result. Okay. Okay. Yeah, now we are going to introduce another really interesting topic in number theory that is called Dirichlet series. So what is the Dirichlet series? Let us define it. So given a sequence, the sequence goes an where n runs from 1 to infinity. Its Dirichlet series, D should be capital. Dirichlet is the series that goes like this: sum of an n to the s, where n runs from 1 to infinity. Okay, and obviously this series does not converge for all values of s. Okay, so and also it may or may not converge, right? Yeah. Can someone tell me an example of a Dirichlet series? Exactly. That's the most natural, yeah, prototypical example of a Dirichlet series, and that is the Dirichlet series of this constant sequence one. If an is one for all n, then the Dirichlet series is sum of 1 over n to the s, right? And this is zeta of s, obviously for real part of s being greater than 1. Okay. Yeah. And yeah. So in combinatorics and in analysis as well, what we do is that given a sequence, we consider the generating function or the power series associated with that sequence. So you can say that power series and Dirichlet series have many things in common. Okay. So let us state what the common things are, and also obviously not everything are common. There are some differences as well. So let me write them in parallel. So in analysis and in analytic number theory. So in analysis we have power series, and in analytic number theory we have Dirichlet series. Okay. Now let's say we have a power series that goes sum of Cn z to the n. Okay, and it converges for, let's say, z equals to z naught. So what does it imply? So this is a power series that converges. What am I drawing a circle? That converges, let's say, here. So what can we conclude from this? That the radius of convergence of this power series is at least this length, right? And in other words, the power series converges everywhere in this open ball. Furthermore, that convergence is both absolute and uniform. So, yeah, absolute and uniform convergence on the open ball Z such that, right. We also have a very similar result in Dirichlet series that goes like this: sum of n to the s converges for, let's say, s equals to s naught. Then what do we have is that then it converges uniformly in this following subset of the complex plane, that is S such that the real part of S is at least the real part of S naught. So visually speaking, if this Dirichlet series converges at, let's say, this point, then everywhere in this uh, right half plane, everywhere in this right half plane, this Dirichlet series converges uniformly. Okay, can someone tell me if whether we have absolute convergence for this, like just convergence for S naught, does it imply absolute convergence? Do we have a counter example? Yeah, no is the correct answer. Okay, yeah. Let me state the counter example. That counter example is, I forgot its name. Is it alternating zeta function? That is, the sum is -1 to the power n minus 1, n to the s. I think it's called alternating zeta function. Like this name makes sense, right? Alternating zeta function. And this converges for real part of s greater than 0. But it only absolutely converges for real part of s greater than 1. So only convergence does not really guarantee absolute convergence. But in the case of power series, we have this really helpful result that we don't have right now, sadly. Yeah. Yeah. Also, the Dirichlet series for zeta function, that is zeta of s equals to sum of 1 to the n over s, the sum over all the n, is defined for real part of s being greater than 1, right? And it has a analytic continuation. Analytic continuation. And that continuation, is it everywhere on the complex plane? Actually, it's not.
Without the one.
Yeah, without one. So analytic continuation in the complex plane except one. Okay. And the analytic continuation has this very, very nice functional equation. That functional equation is zeta of 1 minus s is equal to 2 over 2 pi to the power s cosine of pi s to the divided by 2 gamma s zeta s. Yeah. And using this, using this functional equation, we can find the value of, let's say, gamma of -1. What is it? It's 2 over 2 pi squared, that is 4 pi squared. What is cos pi? Cos pi is -1.
Yeah.
-1. And gamma of 2, what is gamma of 2? Gamma of 2 is 1 factorial, right? Yeah, and zeta of 2 is pi squared over 6. So it's -1 over 12. Mhm. Yeah. But of course, this does not prove that 1 plus 2 plus dot 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 this is negative 1 over 12. It's not. Like zeta function is defined as this sum only when real part of s is greater than 1. And otherwise, zeta function is defined like this. So yeah. And we can make this functional equation look way cleaner if we define the zeta function like, if we define the completed zeta function. So what is the completed zeta function? Completed zeta function is defined like this. So z of s is equal to pi to the power negative s over 2 gamma of s over 2 zeta of s. So if this is true, so sorry, if this is how we define the function z, then z has a very clean functional equation, that is z of 1 minus s is equal to z of s. So as you can see, it's way cleaner than the previous functional equation we had for zeta. Like that's the only purpose of this completion. It's not really completion per se, but yeah, it's just named completed zeta function. Yeah. Well, if yeah, that's a very interesting question and left as an exercise. Hmm? Of course, they're the same zeros. Yeah, now we are all ready for defining the L function of a modular form. Definition. So let F be a modular form of weight K. Then, of course, we can write it as a Q series. And the Q series starts from 0, right? And the L function of F is L of F comma S is equal to, it's a Dirichlet series, right? So we are defining this L function as a Dirichlet series. For defining Dirichlet series, we need a sequence. Which sequence do we take? AN. Okay, very nice. AN, n to the S. And this sum starts from 1. No. The L function is defined like this. The L function kind of forgets the zeroth coefficient. The Dirichlet series can be defined for any sequence. So, yeah, we are, for now, we are defining L function of a modular form. You can define L function of other objects of your interest. For instance, people define L function of elliptic curves as well. And it's of no surprise that these two are, of course, related. Okay. Yeah, and for defining the L function of a modular form, what we do is that we take the Q expansion, we kind of remove the zeroth coefficient, then we get a sequence of the coefficients, and using that coefficients we form the Dirichlet series. Okay. Yeah. Yeah, so it seems like L function is forgetting the zeroth coefficient, but well, who knows? Maybe it remembers somehow. Okay, so now it's a natural question to ask that where does this L function converge? Right. So the answer is L of f comma s is absolutely convergent for real part of s being greater than k. Okay, we are going to prove it now. Proof. So earlier we proved that the nth coefficient grows like n to the k minus 1, right? So we shall use this result. So what is sum of n to the s? It's the sum of the absolute value of n to the s is equal to n to the real part of s. So n gives a constant and n to the k minus 1, and this gives n to the real part of s, and it's not an equality, right? So it's c times sum of 1 over n to the real part of s minus k plus 1. So if real part of s is greater than k, then this thing is like greater than 1, right? So this sum converges. So yeah, so you're basically, so the L function is absolutely convergent for when the real part of S is greater than K. Yeah, K is the weight of the modular function. But does it mean that L function doesn't converge for when real part of S is smaller than K? No, it's not. Because this inequality, an is smaller than c n to the k minus 1. This is for non-cusp forms. If we have a cusp form, then we have a stricter inequality. Not stricter inequality, we have a tighter inequality, I'm sorry. Yeah, we have a tighter inequality, so this a factor becomes n to the k over 2. Then, yeah, then instead of k minus 1, we have n to the k over 2. So, and yeah, and we like to prove stuffs for our favorite modular from Eisenstein series. So of course, what we are going to do now, we are going to find the L function of Eisenstein series. And in the L function of Eisenstein series, our favorite things arise. Not the number 12, but other favorite things. Okay, what is the L function of EKS? It's defined as the sum of an over n to the s, right? And what is an? An is negative 2k by bk sigma of k minus 1. So we can take the negative 2k over bk out in front. So negative 2k over bk times sum of n equals to 1 to infinity sigma k minus 1 n over n to the s. Infinity 1 over n to the s sum of, no, let's write it as a double sum. Sum of n to the s d to the k minus 1 d divides n. Okay. Yeah. Now let's write n equals to m times d. So what do we have? Sum, another sum over d. It's d to the k minus 1, d to the s, m to the s. So we are changing the variables of the sum from n to m. Okay. Yeah. Now can you see our favorite things emerging? Sum of 1 over m to the s, sum of 1 over d to the s minus k plus 1. And these are our favorite things, right? We care about the zeros of these functions. Yeah. Zeta of s minus k plus 1. So the L function of the Eisenstein series is the product of two zeta functions. And in order for the zeta functions to be like the well-defined zeta functions, like to be defined by this sum, we need s, the real part of s, to be greater than k. Okay, but yeah. Yeah, we have a very interesting theorem, but I think I'm just going to state the theorem and keep the suspense to prove the theorem in the next lecture. Okay. So that theorem basically, for that theorem we are going to define the completed L function. Completed L function of a modular form of weight k. We are going to define it like this: lambda of f comma s is equal to 2 pi to the power minus s gamma of s, then the L function. It's it's reminiscent of the completed zeta function, where we define the new zeta function like using the old zeta function and gamma function and some factor of pi to the some power, right? So it's the completed L function of f, and the theorem states that uh, wait, yeah, and this function capital lambda is defined for real part of s being greater than k, right? So the theorem states that this has a analytic continuation, an analytic continuation uh, to whole of C, except, can you guess where the analytic continuation fails? No, n is not really related here. K minus 1. No, but very close. This sum converges for real part of S greater than K. So it fails to converge at S equal to K. Okay, except for at worst, simple poles at S equals to K and S equals to 0. And why did I write at worst? Because if F happens to be a cusp form, then the analytic continuation is entire. That means there are no poles if F is a cusp form. So, in other words, if F belongs to Sk, then is entire. Okay, but while defining the L function, we ignored the first coefficient. But F being in Sk depends on the zeroth coefficient, right? So we thought that L probably forgets about the zeroth coefficient. But this tells us that no, it doesn't forget. Furthermore, there is another very interesting result. if a0 is non-zero, well, it doesn't have to be like this. We can compute the residue all the time. So the residue of lambda at s equals to 0 is precisely negative a0. So not only does it not forget, it remembers it very well. Again, the residue of lambda at s equals to k is equal to negative 1 to the power k over 2 a0. So L function doesn't really forget the zeroth coefficient. It remembers it very well. And that is captured by this theorem, that the analytic continuation of the completed L function has residues a0. Okay, so this is a very interesting theorem, and its proof is going to take quite a while. So yeah, I think I'm going to show the proof in our next lecture. That is going to be our last one. Okay, does anyone have any question?